Hi, I'm Dídac Surís, and I will explain our paper, Learning to Learn Words from Visual Scenes. Most current state-of-the-art digital language systems follow an architecture very similar to the one we show in this slide, where the transformer stack gets as input both an image and the text that's related to that image, and it has to output a prediction based on these inputs. These models have achieved very good results in a lot of vision and language tasks. But how far are these models from the linguistic skills of a 3-year-old toddler? We identified 3 key challenges the systems still need to solve. The first one is sample efficiency. While 3-year-olds have heard around a few tens of millions of words during their lives, state-of-the-art digital language models require of the order of billions of words in order to train. Another challenge is the generalization ability. Children can identify objects through a variety of changes like color, orientation, and so on, and even at 16 months, they are able to point to the 2 tables in this scene and realize that they are actually the same object. However, state-of-the-art visual language models have a hard time generalizing to new scenarios. In this example, the system knows what a knife is and knows what washing means, but because it's never seen anyone washing a knife, it cannot predict that the object being washed is a knife, so it predicts wash pen. Finally, the third challenge is that while 3-year-olds are able to easily acquire new words, transformer-based models do not have a mechanism to do so. When a completely new word appears, they are not able to incorporate it into the system. In our paper, we draw insight from toddlers in 3 different ways, in order to try to solve the previous challenges. First, we use visual and linguistic context to learn. Second, we suggest that a strategy for acquiring language, where this strategy is learned by experience, is necessary. And third, we test our model's language abilities by asking it to point. The key idea of our work is to take the state-of-the-art visual language models, as the one we saw before, and add a layer of abstraction to them. Rather than learning fixed representations, we want to learn the acquisition process itself. Looking back at the previous example, we don't want the system to simply learn what stir means, but we want it to learn how to learn what stir means. In order to do that, we have to modify the training setup. In a regular training setup, the model observes many examples during training, one of which, for example, contains chair, and then in testing, it should be able to predict that the masked word is chair. But because we don't want the system to just learn language, but we want the system to learn how to learn language, we turn this setting into a meta-learning one, where every task consists on acquiring new language from a meta-training set and testing it on a meta-testing set. Specifically, we perform meta-learning in the forward pass. The whole episode that consists of the training and testing set is input to the system. Then the system has to learn from the training set, that here we call reference examples, and output the correct answers for the testing set that we call here target example. How do we test whether the model has learned the word chair in this example? Well, the answer is that we ask it to point to the correct answer, which this is one of the insights we draw from toddlers before. This pointing is the loss we use to meta-train the model. We can evaluate the model's language learning strategy in different ways. By asking the model to point to 2 words instead of 1, we can test its compositional reasoning, as we can see in the second example where the composition is stir paneer. As before, the pointing evaluates the forward pass policy of the model and is used to train it. After the model has been trained, it is able to acquire new language in a single forward pass by learning it from the training set and testing it on the target example. In this case, we input both the reference set and the target example, and the system has to acquire the word avocado and show it by pointing to it. We show the top 2 predictions of the system, where the dark arrow implies a higher probability. We can see that the model has indeed learned to acquire new words. Here we show accuracy values when predicting new words. The baselines BERT and BERT plus vision are trained to produce good contextual representations, so they have good results, and adding vision helps improving the accuracy. But when training with our method, the accuracy at predicting new words improved considerably. In this paper, we show similar results for different datasets and also for new compositions of concepts. Finally, several qualitative experiments also suggest a very high interaction between language and vision in our system. In this slide, we show the regions in the image that are the most important for a correct prediction of the masked words. We can see that these regions are indeed the ones that correspond to the word to be predicted, suggesting that visual grounding emerges during the training. Thank you.